Core to this computer. Okay. Wow. Incredibly hard, but I got there. Okay. So, notability. Again, we're going to do the same type of thing. So we'll have some sample size questions and some things like that. So this should roll through pretty quick because everything is super similar. So here we go. Conditions. So again, we're still going to have the same. I won't say the same conditions. We have we have the same in name, but we don't necessarily have the same in value. So here we go. We're still going to have a random sample. From the population of interest. Okay, so in this case, yeah, that's all we need. Now, here's the difference. Number 2 is still going to be approximately normal. However, now I have to remember I'm talking about a mean. So there's, if we go back to actually chapter 5, there's 3 different ways that we can do a normal, approximately normal with a mean. This is where my sample size is greater than 30 comes in. So now we're going to go back to that one. So if we, again, sometimes I would get confused, and I admit first couple of years, I had to really pay attention to it. If my samples of what I was doing, if it's a mean, then my sample size matters, okay, as far as being greater than 30. If it's a proportion, that's n times p, okay? If I had a population normal to start with, then that is fine. Then that means it doesn't matter my sample size. I'm going to be approximately normal. So, and then symmetric data, meaning I have a symmetric box plot. And actually, no, we're going to clear that. Yeah, symmetric box plot. In reality, I would not know it was normal looking. It could be uniform, but we're going to go symmetric box plot. Now, here is the one critical thing that we have to pay attention to, because here we have a one sample Z confidence interval for mean mu. Here in a second, we're going to have a one sample T confidence interval for mean mu. Okay, so this is where we have another check we're going to throw in here. The standard deviation of population is known. And then our fourth one's going to be independence. Now, I struggle to even show us this one just because I'm estimating for mean mu. Now, if I know the standard deviation is calculated from the mean. So I'm not for sure. Basically, we have to go from previous experiences or something like that. So I struggle with this a little bit as why this is even here, but it's here, so we'll talk about it. But again, my standard deviation is going to be known, so that means we're going to go use a Z confidence interval. So since we're using Z, my Z critical values. Remember, if I have a 90% confidence interval, that's when we're going to use 1.64. or 1.65. If it is 95%, that's when we're going to go over and use 1.96. If it is 99% confident, again, that is when we're going to use a 2.58. Okay. All right. So again, in creating the confidence interval, so remember, this is going to be my point estimate. My point estimate is also going to be my sample mean. Again, just defining everything. This is my population standard deviation. And this may be my sample size. And again, this is my critical value. So again, making sure that we talk through all the little things here. Okay, standard error is the same thing as my standard deviation. So because it came from a sample, we're going to make that adjustment. I'm going to highlight this real fast and erase it. But remember, if I have it from a sample, I have to adjust my standard deviation by dividing by the square root of n. Okay. If I include the critical value in all of this, so we have the whole entire thing underlined there. Remember, if we throw in the critical value, now I've turned this into the margin of error. Okay, so that is the difference between the two. We have the standard error, which is going to be my standard deviation, and that is going to be, if I include the critical value, now it's my margin of error. And again, remember, we just have that standard error description and repeated sampling. The average distance between the sample means of the population is, that's going to be my standard deviation. So remember, this is a bunch of means that I've thrown together and done that average. All right. So again, let's look at what we have here. So when we talk about an interval, we had questions about sample size. So the heights of MHS male students is normally distributed with a standard deviation of 2.5. How large a random sample is necessary to be accurate within 0.75 inches and be 95% confident. Okay, so again, because this is, oops, that's a highlighter yet. This is the critical piece. This is the critical piece of information right here, the standard deviation. Okay, I know my population standard deviation, so I'm going to be using Z. Okay, once we start not knowing that, then I have to switch over and use a T, which we'll get to later today. Okay, so again, remember, so my margin of error is equal to the critical value times my margin, my standard error. My standard error is the standard deviation. So then I have to, since it's a sample, I'm going to divide by the square root of n. So that's my margin of error. So we have 0.75 is equal to, I was trying to be 95% confident. So that means my critical value is 1.96. My standard deviation was given to me at 2.5. And we have the square root of n as my unknown. So here's where your algebra skills have to kick in. We'll divide over the 196 first. For some reason, I have all the steps written out here. So we'll go ahead and kick all the steps in. 3827, and I'm not a big fan just because I've done some rounding here, so this rule probably isn't the best. So what's going to happen is these two are going to trade places. So we're going to go ahead and divide that quotient, and then we'll square both sides, and we'll get n equals 42.7. And so that means that n has to be 43 students. Again, with sample size problems, we always round up sample size. Okay, so again, this is not a new skill at all. We did this already. All right, the only difference is we are going to use a different formula for the standard error. We're not doing a proportion anymore. We're doing a mean. So that's, again, the only difference. But okay, so because of that, because we are doing a mean, we're doing so man. Example 2, a certain candy bar is labeled containing 6 ounces of chocolate. The candy bars have a true population standard deviation of 0.228. So again, we went, and this is identified as a true population standard deviation. So that means I'm going to do a Z interval. Mrs. Sapp, who's a self-professed chocoholic, is concerned about the amount of chocolate in her candy bars. She takes a random sample of 36 candy bars and finds that, so I know n equals 36, and finds the sample mean to be 6.018. Okay, so there we have it. Again, because this is an interval, and again, I'm not for sure, again, how you used it in the last time you came through here, but because it is an interval, we are going to follow our panic model. Okay, so our parameter is, we're trying to estimate a mean, find and interpret a 90% confident for the true mean ounces of chocolate in the candy bars. So we needed to define my mean, okay, where mean is the the true mean ounces of chocolate in candy bars. So I suppose I could have gone a ink and really been short with it, but there we go. I actually think that actually is acceptable, but anyway, I digress. We have some assumptions to make. So again, this is P, this is A. Number one is, do I have a random sample of candy bars? So just to highlight, actually as a low light on the test, we have to make sure that we are being very specific on our population. So I got several people on the test for, and actually I can't talk about the test because not everybody's taking it. All right, I digress. I'll stop. Okay, we got a random sample of candy bars. Number two was, is this approximately normal? And again, we have three, last chapter, it was our proportion. So we were always running to n times p. And now I'll make the comment because I remember it. Okay. I didn't count off for anybody doing this. Okay. Because this is my fault for not being, my attention to detail left me last chapter for some reason. When we and I don't want to write a thing on this, but when I have a one sample test, that means I'm going to test against a known proportion. And since I have a known proportion, that means I have to do, and I'm going to erase this, n times p is greater than or equal to 10, n times 1 minus p is greater than or equal to 10. Okay, I'm going to erase those because those are talking about proportions and this doesn't have anything to do with it. But since I have a known proportion I'm testing against, I have to use n times p and n times 1 times p, not successes and failures, okay, on a one sample, okay? If it is two sample, then I'm comparing the two proportions and I don't have anything to compare it against, then I can use successes and failures, okay? But I was not very clear on that. I was probably, I mean, if you go back and look at my examples, I'm sure I use successes and failures in a one sample. And that's just me being not attentive to detail in what I was doing. I was frustrated at myself, okay? Because that was not very good modeling of what we needed to do. All right, approximate normal because n is greater than 30. Now, on the very front, it said we had a third assumption. We have four assumptions here. We had a third assumption that was the standard deviation was known. Okay. I actually don't like to clutter my assumptions up with that because there'll never be a rubric that has you check that. So out here to the side, I'm going to go standard deviation known equals z interval. Okay, I will just do that out there. So that means I'm going to go back to my third one, which is independent. And that is, we're going to assume that 36 is less than 10% of all candy bars. So we have taken care of we've named our parameter, we've done our assumptions, we need to name this interval. So we're going to name this interval as a one sample z interval for means. Okay, so again, our interval, and I'll write it out on this first one. Again, it's the not necessarily, actually, yeah. There we go. There is my interval. We started out, we have a mean of 6.018 plus or minus 1.64. My standard deviation was 0.228, and we have a sample size of 36. So there's my interval written out. Okay. So again, remember, AP wise, we just need that or we need this, but for Mr. Doughty wise, we need both. Okay. And we'll get to a point where we don't need both. All right. So that means that we need to confine this interval. Okay, so I'm going to jump out of my calculator. We're going to slip over here and grab my calculator. And we're going to go to stat. We're going to go over to tests. Okay, except we're going to do now, we're going to scroll down to where it says Z interval. Okay, so I know there's some two sample stuff in there, but the Z interval is what I need. So we're going to select a Z interval. Okay, now this particular one is going to come from data. Excuse me, this one is coming from stats. So if we look here, I have data. Data is pointed towards a list. You can't see me pointing at it, but that means we know a standard deviation and we have a list where data is stored. I'm going to go over to stats, and actually I don't remember on the TI. I don't think that. Yeah. So on the TI, we're going from stats. We're going to arrow down. My standard deviation is known at 0.228. My X bar is coming in at 6.018. My sample size, we know to be 36. My confidence level, I believe it was 95. 90. And calculate. And calculate. So my interval is from 5.956 to 6.081. And again, your rounding is irrelevant. So I'm going to go with 5.96 to 6.08. So now we're going, we have found an interval. And now again, we're back to all that fun stuff. We have to do a conclusion. We are 90% confident. And again, this is where you got to know, you can't, sometimes you just get in a zone and you start doing stuff. We are 90% confident the true mean ounces of chocolate in candy bars is between 5.96 and 6.08 ounces. So now we need to make sure we're getting that context in there. Although we had it back here too, so we're okay. But again, make sure your answer has that context in there. And I don't like that. There we go. All right, there it is. Question B, should Mrs. Sapp be concerned that she's being shortchanged? I'm looking at, oh. What do you think on this one? I have two answers. Sorry, I was looking at my notes going, what do I have for down here for notes? This is crazy. Should she be concerned that she is being shortchanged? And no, because 6 is in the interval. However, part of the interval is below 6. Ounces. Leaving some question. Okay. Moving on up. Okay. Suppose we take a random sample of 32 MHS students who have taken the SAT. All right, so again, we have 32 MHS students, so that means we're going to have a sample size of 32 who have taken the SAT and find that mean SAT score is 1250, so that means we have an X bar. Again, we know the population standard deviation, so that means we're going to standard deviation known, which means we're going to do a Z interval. Find and interpret a 95% confidence interval for the mean SAT score of all MHS students. Okay, so again, here we go. So Mean mu is the true mean. SAT score. Of MHS students. So again, we're, I mean, it depends on how you, hopefully by now we're getting we just know what we need in panic, but panic is what we're going to follow. So again, we've named that parameter. We have our assumptions, okay? Number one is this has to be a random sample of MHS students. Number two is it needs to be approximately normal because n is greater than or equal to 30. And three, and again, I'm shortchanging you because I took care of number three here, but I still just want to go roll with the same ones, independent. And like I said before, the likelihood that we see a z interval for a mean is infinitesimally small, just because if we know the population standard deviation, we're going to know the population mean. Anyway, it's independent. 30. Nope, not 30. 32. Yes, there it is. 32 is less than 10% of all MHS students. Now, this is the kicker, taking SAT, because I am not for sure if we have 320 MHS students take the SAT, but we're going to roll with it. All right, so we're going to name that we have done my assumptions. We need a name next. So again, this is going to be a one sample z interval for means. So we're going to start with that point estimate. The point estimate was 1250, my sample mean. We are attempting to be 95% confident, so that means we're going to use 1.96. My standard deviation was 105, and we're going to divide that by the sample size, which is square root of the sample size, which is 32. So there's my interval. Again, I'm not going to, this is a case where we'd go out to our calculator for time's sake right now. I'm just going to give you the interval. It's 1214 to 1287. And then we need a conclusion. So that means we are 95% confident. The true mean SAT score for MHS students lies between, or in the interval of 1214 to 1287. So this is going to sound much like a hypothesis test, but Mr. Wishman claims that the mean SAT score at MHS is 1290. Do we have sufficient evidence to reject his claim? And in this case, yes, we do. Because 1290 does not lie in the interval. Okay. I forgot to load this, didn't I? Okay, so before we do the one sample t confidence interval for mean mu, we are going to talk about. I can't decide when to do this. All right, so a t interval, and this is my bad for not pulling this up earlier, and I don't know. I don't think I have this in my notes anywhere. So we'll just jump out on the web. Uh-oh, you can see that I cheat when I place words with friends. Scrabble word finder. All right, so we're going to add. Okay, so we're just going to Google a T distribution. Go look at images. Oh, actually, we didn't have to. Okay, so here's the image I pull up all the time anyway. Okay, this is a T distribution somewhere. There it is. Okay, so there's our T distribution. Okay, so what happens is when we have a standard Z, which is the blue line, is what we usually follow. That is my normal distribution. It is a little bit over dramatic as far as that goes. What happens is that T distribution puts more area out in the tails. Okay, and it allows us to do stuff when it's small. So what happens is, wow, I don't want that. So what happens is start clicking stuff. When my sample size is less than 30, that puts more area out in the tails, allowing us to be, it's going to increase, that forces my critical value to be larger, and therefore we're going to, that's going to extend my confidence interval. It's going to make my T values much larger. So when I go to find that value of a T, my P value, that will be a larger p-value, making it harder to reject my null hypothesis. But what happens is, as my sample size increases, we're going to get a larger and larger and larger value. So if I come back out here and I go back to Notability, and we go back to my formula sheet, in my formula sheet, we have a Z table, which is table A, but if we also scroll out here, we have table B, which is a T distribution, okay? And what happens is we have what's called degrees of freedom. And the degrees of freedom is all tied into my sample size, and that is what's going to give me my critical values here. And we'll talk about more how to use the table later. I'm just saying a T distribution is like a Z distribution, except it's going to be wider. And as my sample size increases, it becomes more and more like a Z distribution. So real fast, just to come down here. On our last problem, we wanted to be 95% confident, which is going to be right here. Okay. However, remember, if we use something that's 95, if we look at this, my sample size is infinite, and I come over here to 1.96. Remember, the critical value that we use for a 95% confidence interval is 1.96. So there it is. I mean, we actually have your critical values are here. If we use a 90% confidence interval, it is there. And then sometimes we use 99, which is 2.58, which is that guy there. So you no longer actually have to remember your critical values for your Z intervals, because if you go to a T table, they're actually there. So it's just remembering that fact. All right, so let's go back out to our notes and see what we can do with our notes. And I did not appear to have named this yet. So hold it before I forget, because if I save it back without renaming this, it's going to go right over the top of something I didn't want it to. All right, so there's the key. All right, so here we are. We're in our T distribution. So we're going to be basing this interval off of a T distribution for mean mu. Okay, so what happens is we have a one curve. It's going to have 1 degree of freedom. We're going to have a second curve. It has 2 degrees of freedom, et cetera, et cetera. Okay, so the T curve is corresponding to any fixed number of degrees of freedom, is a bell-shaped curve and centered at 0, just like a standard normal curve. Just the T curve is going to be more spread out than the Z curve. As the number of degrees of freedom increases, the spread of the corresponding T curve decreases. So again, as the smaller my sample size, the wider the curve is. And the more closely that T curve resembles a Z curve. And my degrees of freedom is going to be my sample size minus 1. Okay, now here again, if I know my standard deviation, I'm going to use Z. If I do not know my standard deviation, we are going to use T. Okay. So let's see what we can do here. So find the T critical value for 80% confidence, n equals 15. So let's talk about if we draw ourselves a picture, the picture is still going to be the same thing. I want to be 80% confident. So I know that in here is going to be my 80%. Okay. So that means that down here, we are worried about this area here, which means that I have 10% left over. Okay. But what happens is now my degrees of freedom is going to be equal to 14. Okay. So the two ways to do this are, we can go back to our table. So we said my degrees, it was a sample size of 15. My degrees of freedom is 14. So here's 14. Okay. We decided we needed a 10% tail, right? So it was 80% confident. So there's the column that I need. And it looks like my answer here is 1.345. If you forget your tail, if you just come down here, we were going to be 80% confident. Okay, so that identified the column as well. So I know my critical value for doing this test is going to be 1.345. So moving on, the next one, again, we're going to be 95% confident. So we're going to make this wider. I'm going to be more confident that I encompass the true mean. That means that over here on the left-hand side, we're going to have I'll write it as a decimal this time, 0.025. And I know that this is going to have 23 degrees of freedom. Okay, basically it's your sample size minus 1. And we're going to do this one the other way. We're not going to use the table on this one. We're going to use our other device, which is our calculator. Now we're going to go into that distribution area. So you're going to hit second in vars. Okay, and we're going to choose a TCDF. Wrong answer. That's not what we're going to pick. We're going to choose, we want the critical value. So now what we're going to do is inverse T. My bad. So the area that we want to encapsulate is not actually, it's so that's that left-hand tail area. So this is where it's important to actually understand a left-hand tail. When you do an inverse norm, you got the left, center, and right. You don't get that option probably on a T. So we know that my left-hand tail is going to be 0.025. My degrees of freedom was 23. So we can paste that in there. Why did it jump back to this? Oh, clear. I know what happened. I forgot to quit. Okay. I don't know. Clear again. All right. Sorry, I didn't mean to sigh in the microphone like that. So if it had just gone to our table, we'd have been there much faster. Anyway, we're going to do an inverse T. It came out to be a negative 0.206. Now, remember, we're talking about a critical value for a confidence interval, so the sign is going to be completely irrelevant. So 2.069. However, if we'd gone, so I'll write this down. If I'd gone back out to my table and we'd gone back into my formula sheet, what was it? I've forgotten. It was 0.025. So we had 23 degrees of freedom. So we're down here on 23. We were trying to be 95% confident. So here's 95. So 2.069 is going to be right there. So that's where we're at. We wrote down the right number. Again, it was probably almost faster to go to my table to get that critical value. Okay. All right. Back to our notes. Okay, fine. We'll do it that way. Back to our notes. Oh, man. Struggle bus. Driving it good today. Last one, again, is a curve. We're still 95% confident, which means we have a tail of 0.025. My degrees of freedom is going to be 199. Okay. And we're going to get a T value for that. And I won't cut to the chase. Anyway, I'm going to write it down, 1.984. So let's go back out to my t-distribution just to explain. Now, the thing is, my degrees of freedom is 199. Well, where does 199 fit in from? So we're always going to round up to the nearest one on the table. So that's why I would use row 100. So for example, let's say my degrees of freedom was 65. I'm going to use row 60. Okay. Or if it was 70, I'm going to use row 60. Okay. So I'm always going to move up and use that row. And that's why sometimes the calculator is the better option. We just have to understand how to do that. Okay. So with the calculator, again, for that, this is going to be the inverse T. And then we have the area. And we have the degrees of freedom. Okay. All right. So again, all of this, if we look at the interval again, the interval again has the same exact construction on page 1, except now we're talking about a critical T value. All right. So again, your assumptions are still the same exact assumptions. So, for time's sake, I am just going to refer you to page 1. All right. They're the same exact. Okay. Except for if we were actually following along from, let's go up to page 1. Where's page 1 at? Clear up here. Step number 3 was the standard deviation of the population is known. Standard deviation of population is unknown. Everything else stays the same. So I just have to recognize that I have that. So therefore, if it is known, this means I have to use the T critical value. If it's unknown, excuse me. Everything else stays the same. Okay. So we have one more sample to go, and then we'll see if we are going to take time to do the activity or not. All right, so we have 10 randomly selected Woodrow Wilson students. Each were asked to list how many hours of television they watched per week. The results are, it says find and interpret a 90% confidence interval for the true mean hours of all of students of watched per week by Woodrow Wilson elementary students. Okay, so mean is the true mean number of hours. So we're gonna, man, it feels like I'm cheating when I do that. But it spares you and me writing it all that out. Okay. Here we go. So again, this is an interval, so it's panic. We've identified my parameter of interest. My assumptions. Random sample of Woodrow Wilson students. Done. Okay, here's where it's going to get a little bit tricky. Approximate normal. Usually when we go with approximate normal, we're running home to, hey, do I got greater than 30? And in this case, I don't have greater than 30. So I have to have some other method. Okay, method number 2 is my population is normal to start with. And I can't do that one. So now it has to be my box. I have a symmetric box plot. Do I have a symmetric box plot? Well, in this particular case, I am left with a hard list of numbers. So we're going to have to run back out to the calculator. And we're going to have to put a list in my calculator. And I put mine in list 3 because I have some other stuff. Yeah, anyway, it doesn't matter. So I hate to see you actually enter data, but I figured I could enter these 10 pretty quick and it wouldn't be too painful. All right, so I'm on cell 11, so that means I have my 10 numbers. And if I go back up there and check, it looks like I think they're all entered correctly. So first thing is, so again, if I have data, I'm going to go look at my box plot. So I'm going to go second, I'm going to go plot. I'm going to go into plot number 1. We're going to arrow down. I need to turn this into a box plot. My data is stored in L3. And then we're going to zoom and stat. So there is my box plot. So when I do this, as long as, in reality, the box plot is bad, just because it could be, a symmetric box plot could actually be a uniform distribution. So you could go back and as well on number 1 here. Let's see what I have. I don't know. Thing is, it's going to be way ugly on this machine. Okay. Again, this is, and it's ugly just because I have very few pieces of data, but we'll go back to, sorry, I'm babbling. This is not a normal looking distribution. Okay. So we're going to roll with the symmetric box plot and we'll move on. Now, the thing is, you actually have to sketch your box plot. Since my standard deviation is unknown, that means we're going to construct a t interval. And again, that was just I wrote that now because that's my third assumption. I just don't like to put it in with my assumptions. And then lastly, we have independent. And I'll assume there's more than 100 Woodrow Wilson students. Are any of you a wolf? Is it wolves? Woodrow Wilson wolves? I don't know. Okay. Again, we're panicking. Parameter taken care of. Assumptions taken care of. Name. So again, my name has changed. A one sample t interval for means. So we'll do this a couple of different ways. Number one way is we'll just go ahead and do a one. We'll go ahead and go out back to my calculator, and we're going to quit this. And I'm going to go into stat. I'm going to go over to calculate. I'm going to calculate that one variable statistic on L3. And I'll have all the different pieces, parts that I need. Okay. So if I scroll back here, I could list all these pieces out, meaning X bar is 10.7. My sample standard deviation was SX, and that's going to give me a 3.43. My degrees of freedom, I would need to know that to construct my t interval, okay, is n minus 1. So that means we're going to go with 9. N equals 10. That doesn't really look like a 10. And then that means if I use it's 1.83. So I have my interval will be 10.7 plus or minus. My critical value is 1.83. My sample standard deviation is 3.43. And we're going to divide that by the square root of 10. And there is my interval as far as that goes. Now, I'm not, this is all the stuff, this stuff, I don't necessarily need you to write out. I just wrote it out to help organize the problem when we wrote it down. In reality, here's what happens. You write down, that's a one sample t interval for means. I'm going to go back to my calculator. I'm going to go stats. We're going to go over to my test, except now instead of doing a z interval, now we're going to do a t interval. So I'm going to select t interval, except this time we have data to work with. So I'm going to highlight data. Now notice that my standard deviation went away. So I'm going to arrow down, arrow back up, clear. My data is stored in L3. So it's going to go check everything for me. I just have to tell it how confident I want it to be. And I've forgotten how confident we're supposed to be here, 90%. So we're good. We're going to calculate that. We're going to hit the enter button. And what in the world? Try again. Okay, there it is. 8.71 to 12.69. So again, my conclusion, again, we've named it. We came up with an interval, and now we're ready for a conclusion. We are 90% confident. The true mean number of hours of TV watched per week by Woodrow Wilson students is between 8.71 and 12.69 hours. And again, I'm double dipping on the units, but that's okay. We want to make sure we get hours in there. All right. Suppose the principal at Nora Woodrow Wilson claims that students at Woodrow Wilson watched 9 hours of TV per week. Do we have sufficient evidence to reject her claim? And again, that would be no, because 9 lies in the interval from part A. All right. We have hit the first 4 pages of notes, which is where we wanted to be. The question is, there was an activity that we would have done in class, that we will do in class, that has to do with the number of states that we can name in a minute. But do I take time to do that with you guys? Do you want me to do it with you? So I put you all to sleep, or nobody cares, or nobody wants to answer. All right, so I'm going to stop the recording because I don't need that anymore.